Okay, welcome everyone. My name is Alex Bayen. I'm with the Intelligent Infrastructure Clusters here at CITRIS. It's my pleasure to welcome you to the seminar. I want to say hello to our web viewers. We will have our usual IM system. If you want to ask questions, you can type them to us, and we will be able to read them to the speaker at the end. I want to also thank Infion for the lunch. In fact, if you are a web viewer, you should know you're missing a really, really good lunch here. I also want to say next week is spring break, so we won't have a research exchange next week. Two more announcements. If you're coming for the I for Energy talk this week, it will be in room 250, not in this room. And finally, if you're a student, the deadline for submitting the white paper for the big ideas is coming fairly quickly. It's on March 19th, and there is a $30,000 cash reward if you win that. So I think this is the time to write a really cool idea in a white paper and to win that one. So today is my pleasure to introduce Professor Per Enge from Stanford University. So Per is a professor in the Aeronautics and Astronautics department, where he's the Kleiner-Perkins professor in the School of Engineering. Per has been also the director of the GPS lab at Stanford, and anybody who has been at Stanford and has visited the lab has seen the unbelievable achievement that this lab has accomplished for decades there, and I think we're going to hear a little bit about this today. So among all the other awards and distinctions that Per has received, he's a fellow from the IEEE, and I think the title of the talk today will be Security for and from GPS, which is one of his areas of expertise. So please join me in welcoming Per for this talk.
Thanks, Alex. It's very nice to be here today. I want to take a moment to thank my hosts. Alex Bayen, who is known to you, came by and talked about the mobile millennium at the Stanford Symposium for Position, Navigation, and Time. And I think it's the 150 sharpest people in GPS were in the audience, and they were just blown away. They loved that talk. That was a fantastic talk and great and imaginative work. So thank you for inviting me. My other host is David Stark. Give a wave, Dave. Dave is the managing director of Stiles Hall. And I don't know if any of you are familiar with Stiles Hall, but I would encourage you to find out about it. It has an incredible history of service to the community and the university, and so if you look that up on the web or want to talk to Dave, I really, really recommend it. Thanks for hosting me as well, Dave. Talk about GPS, talk about security, both for it and from it. For a long time, it was impossible to talk about security from GPS. It's itself so fragile that why would you actually want to try and lend security to something else? But over the past few years, the technology for making GPS stronger has emerged, and so now we get ambitious and say, perhaps it's so strong that we can actually lend some strength to other applications. Here's the picture, and the GPS constellation is on the left there. Today we have 30 satellites that are operational on orbit. We have a couple of other ones up there that are a little bit sick, but that's okay. With 30, we have plenty of geometric strength. You seek, to have 4 of them in view. You measure range to those 4 satellites, and the term of art is that you quadrilaterate. With 4 range measurements, you can solve for your X, Y, Z. And oh, by the way, the user clock is not synchronized to GPS time, so we augment the state, and you have to go after that and solve for that as well. So the system is based on atomic clocks carried by the satellites that make sure that that transmission is exactly on time. Signals come down. Here's my favorite application, landing airplanes. And the rays come down. Generally, you have 6, 7, or 8 satellites in view into an antenna mounted on top of the fuselage, and the arrival time is measured with the local clock. In terms of foreshadowing where we're going in this talk, you can see the frailties immediately. These satellites are in medium Earth orbit, so by the time the signal travels 20,000 kilometers to the surface of the Earth, it's pretty weak. As a matter of fact, it carries a power of about 10 to the negative 16th watts. Negative 160 dBW can be readily overwhelmed by an interference source in the neighborhood. The other thing is spoofers will sometimes set up, and their goal isn't to just jam your signal. Rather, it is to inject a signal that misleads you. You accept it as being legitimate and authentic, and it turns out you're not where you thought you were. So those are our topics down the line. Oops, there we go. So here are the essential ingredients of GPS replicated. Time of transmission, synchronized to GPS time. Oh, we need to know where the satellite is. So orbit determination to the 1 meter level at MEO was developed for GPS. It was a feat in of itself. We do count on knowing the speed of the wave. So we more or less assume it's the speed of light, but the troposphere and ionosphere intervene to make that a little bit difficult, but that's okay. We model that or have developed techniques to take out those delays. So I think we're okay with that. And then we measure the time of arrival. So those four things, as well as a multiplicity of satellites, are the essential ingredients of GPS. Generally, all those things go well. And when they do, we talk about an east-north scatter plot that looks like this. You can see the error is bounded by about 5 meters. And that's the nominal performance that we get day in and day out. Let's take a little bit of a longer view. Let me give you a nickel history of the technical evolution of GPS, starting with availability, accuracy, safety, coverage, and security. By availability, I mean the first decade of GPS, the 1970s. We were just desperate to get the satellites on orbit and reasonable user equipment available for demonstrating the system. So it was just a matter of getting the satellites up there. Accuracy. This was the great enterprise of the 1980s. For civilians, it was dominated by selective availability, a program where the DoD intentionally degraded the accuracy of GPS. In that decade, we started to work on and developed differential GPS, which works by the simple expedite of putting a receiver at a known location and then broadcasting the differences between what we see for GPS and what we know must be true. And those are corrections, and they improve the accuracy greatly. By the way, they obviated selective availability, and in the fullness of time, Department of Defense turned it off. It really had no further effect. It wasn't being effective. Safety, well, we'll get to that. Let's start with availability. Here's the growth of the GPS constellation. First 4 satellites in 1978. If you contrast that early GPS program office to the amount of effort and time required to put satellites on orbit these days, it was amazing. Colonel Green, from the time he was authorized to do the satellite build to the time of launch, three satellites on orbit, only 3 years lapsed. So that was an extremely effective program office. And the stories of their efficacy are great and great to listen to. Anyway, constellation built up. There we are with 30 healthy today. At the same time, the user equipment was getting smaller, lower power, lower weight. When they began the GPS program, they estimated that they were going to build a total of 40,000 receivers. That was it. That was for all the ships, tanks, foot soldiers, aircraft. 40,000. And based on that, they sold the utility of GPS. Today, we manufacture 10 million receivers per month. So the tail now wags the dog. The civil use has, in that way, overwhelmed or overtaken the military use. We still have any number of issues about managing a dual-use system. It's not an easy thing to do. But there you have it. I think this is a complete GPS receiver, maybe built on a Theros or Surf. I don't know which one of the chip merchants gave me that image, but there you have it. It's a tiny little thing. And the total power draw is around 20 milliwatts. And they have now gone to full integration onto one die. So that's all in the cards today. Here's the accuracy story. Until May of 2000, we had this intentional dithering of the satellite clocks. In May of 2000, that was turned off, and today we enjoy accuracies of around the 5 meters that I showed you. The selective availability was turned off for a couple of reasons. One is it had no longer any real utility because you could use differential GPS and get whatever accuracy you wanted. The other was it was turned off at that moment because the U.S. wanted to persuade the Europeans not to go forward with a competing system called Galileo. And I think the first line of reasoning was solid. The second line of reasoning, it didn't dissuade the Europeans at all. They've gone ahead with Galileo anyway. And here's the accuracy viewed as a scatter plot. This is if you have a cheap receiver, let's say the thing in your cell phone, and over here, if you pay $500 for that receiver and get something that has better precision, lower noise, and so forth, the scatter goes from plus or minus 10 to down to plus or minus 5. If you want better accuracy than that, you can do differential GPS. This is the concept I just mentioned. We put a reference antenna at a location certain and broadcast the corrections these days into all kinds of applications. Harbor entrance, aircraft landing, and so forth. So here's the scatter. And this is just the earlier plot replicated. And here's differential GPS, and you can see the kind of factor of 3 or 4 improvements you get in accuracy. When I was earning my tenure, the Department of Defense still had selective availability on. So the scatter plots were much sharper. In contrast, the one over on the left had a scatter of plus or minus 100 meters, and it went down to about 1 meter with differential GPS. So I claim I am the one person on the surface of the Earth who feels sentimental about selective availability. It was a very, very good thing for me at the time because I could show this factor of 100 improvement, and it looked pretty shocking. But I'm probably the only person who misses it. Let's move on to safety and coverage. Safety is the enterprise of paying attention to the outliers. It's not about the core of the distribution. It's totally driven by the outliers. And that was the big enterprise in terms of development of the 1990s. And it goes back to this picture I showed you. If you're a safety engineer, you deconstruct the GPS function and you seek fault mechanisms or rare normal conditions that can sneak into any of those things and disrupt them. So this is the enterprise of our Federal Aviation Administration, let's say, or internationally ICAO, International Civil Aviation Organization. And the biggest enterprise of the GPS laboratory over the past 15 or 20 years has been to understand the pathologies associated with each of these. In terms of spoofing and jamming, the attack, for the most part, is on this function. Even though you can imagine other things going on, but the attack rises there. Here's a famous incident, April 17th, 2007. They wanted to reposition one of the GPS satellites. which is fine. They can move it around in the orbit if they want. But generally, we expect and hope that they set the satellite unhealthy before they do that. So in this case, it was still flagged healthy, and the satellite moved. If you used it, you could suffer errors of around 60 meters or so, and you can see the data showing what happened to the unprepared and unprotected user in that case. This is the same scatter that I showed you earlier, but now it's contained in the upper right-hand corner of the overall plot. In the history of GPS, we've had about 70 such incidents. Either a fault in the system or a powerful so-called rare normal condition that has so degraded this assumption that we get large errors, unexpectedly large errors. We call them HMI, hazardously misleading information. It just means that the airplane may be somewhere other than you think it is, and the difference is so great that you should worry about it. Just to normalize you, that distance to that distance is about the width of a runway. So this would mean that you would land in the field next to the runway. So the big systems, well, here's just to tweak your imagination a little bit. This is Sitka, Alaska, where we did a lot of our flight trials back in the 1990s. And it's a beautiful area, but generally the weather is much, much worse. So if you can imagine approaching this airport on a dark and rainy night and being 60 meters off to the right, you're in the drink.
Bridge to nowhere.
Yeah, yeah. That is a good runway for a Navy pilot, for sure. And so what the augmentation systems do, there are really two. One is a continental kind of architecture called the wide area augmentation system. And they tighten up the core of the distribution. They do include differential GPS corrections, and that's a good thing. But it's not the main purpose of either wide area or local area augmentation. It's just to get rid of the red stripe. That's why they're there. To detect those rare normals, to detect those faults, and protect the user from their effect. The other big enterprise that followed the safety enterprise was coverage. So this is a very different community that works on this. The aviation stuff is worked on by the Honeywells, the Raytheons, Canadian Marconis of the world. Coverage, because it's for your cell phone, is worked by the Qualcomms, the Broadcoms, the Theroses of the world, the chip merchants. And their problem was, well, people wanted to have the same accuracy downtown and indoors that they get under the open sky. Or they wanted GPS to work whenever their cell phone worked. Neither one of those things is easy. So what they had to do was assist the cell phone. In other words, send you information over the cell phone link that helped you get the GPS navigation data in quickly, so you didn't have to wait for the satellite to send you all the supporting data, and at the same time helped you integrate for a longer time so you could have a better sensitivity. And in fact, the normal GPS receiver works well down to a power level around the negative 160, but an assisted GPS receiver can work all the way down to negative 190 dBW. So they found 30 dB, roughly speaking, of gain through those techniques. Now, we turn to the topic at hand, jamming and spoofing. I'll put this photo back up for you. And jamming just leverages the fact that the satellite signals are weak. If I have jammer that has about the power of a cell phone, I can jam GPS operations for 10 kilometers fairly easily. And the fact of the matter is, we're under jamming attack all the time. If your car is stolen in Europe, it is standard operating procedure to drop a jammer into the stolen car, because it will knock out the GPS reception. Oh, by the way, it also knocks out the cell phone transmission, so your OnStar or your Locata, whatever it is that you have in your car, won't work. Thieves will be able to take your car. So we shouldn't regard this as being speculative or something that might happen someday. It's, in fact, there all the time. The spoofer, as I mentioned earlier, is the one who puts up mock signals. So as you're approaching here, maybe they'd like to try and persuade you that the airplane is other than where you think it is. Now, it turns out that's a lot more difficult. To build a jammer is about $10 worth of parts and an afternoon worth of work. To build a spoofer is a big deal, because the GPS receiver isn't that naive. If all of a sudden your position steps, and that step is incongruent with the dynamics of your platform, you kind of know something's a little fishy. Or if the spoofer all of a sudden has more power than the GPS signal that you expect, you notice it in automatic gain control of the front of your receiver. So there are a lot of kind of frontline things you can do to fend off spoofing, but people are getting more and more elaborate. The folks from Cornell briefed quite a competent, capable spoofer at the big GPS show in September of 2008. So let's talk about this. Now, what's the FAA doing? I'll give you this as the first case study. And the good news is the FAA is the most conservative organization that I've ever been part of. And even though GPS has been with us for 20 years, and the wide area augmentation system has been operational for 7 years, they haven't turned off a single nav aid. They've kept all that infrastructure in place. And it's partly driven by this worry that someone might be able to knock out GPS. So today, they still have the full complement of so-called VORs and DMEs that they had at the beginning of GPS. VOR, VHF omnidirectional ranging, it's a bearing system. DME, distance measuring equipment. It's a ranging system. Now, DME, kind of depicted here, is kind of kin to GPS because it's based on lateration, measuring range, but DME is a round-trip system. So we initiate in the aircraft, the air signal comes down, the ground system receives, and within a delay certain, response. Reply, response. We call that two-way ranging. It's a beautiful thing because when you're just measuring that round-trip travel time, you don't have to worry about the clock offset either here or here. Those things can be way out of synchronism. This thing does not need to be synchronized with that. After all, you're just measuring the round-trip travel time, so you're kind of good. That's a strength. The concern is that all your users are radiating. So where we're going with this is we're wondering, well, maybe we should keep DME in place. By the way, we'd like to turn off VOR. That's the more expensive of the existing ground infrastructure. So can we keep DME in place and count on it during a jamming event? So that's the thing that we're contemplating right now. And the risk rather, one of the advantages is that the avionics exists, the ground system exists. We'll probably have to augment it some. We may require new avionics in the airplane, which is a frightening prospect because the cycle times up here for equipment are supposed to be around 20 years. So if you go out to that community and say, oh, you have to swap out everything, they're not happy with you. The concern is that if we do have a jamming event, and let's say it's a dark and stormy night, and we have 100 aircraft over the Bay Area, and they all of a sudden light up their DMEs, what happens to that multiple access problem? Will we really have capacity to bring all those airplanes to the ground? So that's the worry. So the thought is, why not keep some of them in the round-trip mode so we can solve for the clock offset up here and have the other ones just broadcast a heartbeat. So it's a one-way ranging, hybridized with two-way ranging. Architecturally, that seems to make sense. It solves the capacity problem. It still looks pretty accurate. So that's where we're going. The thing that it does require is, even though the round-trip ranging eliminates the clock offset up here, we now do have to synchronize this guy to this guy. And if you go into the community today and say, how would you synchronize two transmitters separated by 100 miles? They say, oh, use GPS. And that's not such a hot idea when you're in a GPS-denied environment, so the research is directed at that. I think I have some plots here just to bring this close to home. Here's the Bay Area. Here's Woodside DME, Salinas, I think maybe it's this one. And I'm sorry, the red are DMEs, and the blue are potential additional ground transmitters called imaginatively ground-based transmitters, GBTs. And they're there because people are thinking about expanding how we do surveillance in the airspace as well. So that's part of a program and an idea called Automatic Dependent Surveillance Broadcast, ADSB. And you might think, well, Pierre, look, I thought you were trying to get rid of ground stuff. And now you've added a bunch of red stars here. Aren't you working against your own purpose? And the neat thing about the red stars is that those transmitters are co-located with cell sites. So there's the inspiration or the depth of that idea, is we're going to turn off federal sites. And since we're only interested in this as a backup function, these sites, the fence is already there, the power is already there, the real estate is already there. Anyway, let's go on and see how this works. The big issue for terrestrial radio like DME is propagation across the terrain and coverage at low altitudes. So here's a chart of our bay. And the dark green means that the service is good enough to provide navigation to the aircraft on airport approach. That's what we care about. We know we can cover them when they're at high altitude, but we need to get them back on the ground if there's a GPS jammer. And so the dark green, the prevalence of the dark green is helpful. We have to start to superimpose on here all the approach pathways for SFO, Oakland, and San Jose. But that's the kind of thinking we're doing here. The next chart is just for an improved version of DME, and things get even better. The dark blue means that we can bring the aircraft even to a lower altitude. So this is a risk consideration. We're worried about getting the fleet back on the ground. And by the way, back up in the morning, even in the presence of a GPS jammer, and the better the guidance, the worse weather you can tolerate. So we should return now to the question of the time transfer. Remember, if we're going to use that hybrid solution to get away from the capacity problem, we do have to synchronize the transmitters on the ground. And the idea here does fly in the face of reasonability. It says, hey, look, let's not give up on satellite navigation that readily. After all, we really just want to transfer time in regions of a few hundred miles across throughout the US. As part of WAAS, we put ranging onto commercial geostationary satellites. That ranging signal is under FAA control. It's not under DoD control. So even if you had some kind of systemic failure of GPS, we could make sure that the WAAS signal would continue to radiate. Now, it turns out it's right in the L1 band. So if there's a very strong jammer right at L1, still doesn't sound like that great an idea. It's going to be right in there in terms of the same spectrum. So what we're planning to do is leverage the fact that the DMEs are at fixed sites. So what we're going to do is put a beam steering antenna there. And this is a larger thing, maybe a little bit larger than one wavelength across. GPS wavelength is 19 centimeters, so something like that. And put, let's say, 7 or 9 elements, antenna elements, on that plate and control the received phase from each of them so that we're placing a heavy beam on the geostationary signal and discouraging the signals that come from the horizon, the jammer. There's a good reason to do that. The most effective thing to do against a GPS jammer is to build a controlled radiation pattern antenna. You can't afford to do it for your handset because the antenna is that big, but you can afford to do it for a fixed site. So we're interested in doing it. Here's the block diagram. If you go through here and you do the link analysis, you'll discover that you have about 60 dB of AJ margin. So you're suppressing the interfering signal by a factor of 1,000,000 in power. And so the radius of effect of a jammer has become that much smaller. Or, if they really want to cause you trouble, even so, they'll have to radiate so much power that you can find them very quickly. So that's the hope. Please know this is kind of a radical perspective. People, in general, their reaction is, hey, look, GPS is denied. Don't count on anything good happening in that band. So this is a little bit out there in terms of our proposals, but we're having fun with it anyway. Okay, let's turn our attention to spoofing. I think I have about 10 minutes left and 15 minutes left, and that's about right. Spoofing is also on the rise. Amongst the 500 million users of GPS, a good fraction of those are involved in location transactions that are associated with value, either safety or financial. Here's an example. This is the Marine National Park to the west of Hawaii. I've heard the numbers, and there's just an enormous number of fish who breed along that reef. And since it's a national monument, and because we want those fish to breed in peace, it's illegal to fish in here. Even so, oh, and by the way, we monitor for poachers using surveillance satellites that fly over in low Earth orbit. Unfortunately, the poacher will sit right here, and they have the ephemerides for the surveillance satellite, so they know when the surveillance satellite is above and sets. The moment it sets, they carve in here, and in about 90 minutes, they can take $60,000 worth of fish. So we'd like to require them to carry GPS and report to us their position. Now, of course, if you're going to take $60,000 worth of fish in 90 minutes, maybe you have the wherewithal to hire some poorly directed engineer to put a GPS signal simulator on your boat. I'll tell that GPS receiver exactly where I want it to be. And so that's the spoofing issue in one example. We have another one coming up. Countermeasures. This is all listed and nicely described in this nice paper by O'Hanlon. Appeared in GPS World back in January of 2009. And this amplitude discrimination I told you about, if all of a sudden that signal comes in and it's stronger than the GPS signal. And by the way, the GPS signals are in a fairly tightly controlled band in terms of their amplitude. So you better get that just right in terms of spoofing. If you don't, I'll see my automatic gain control jump, and I'll know something's worrisome. Time of arrival discrimination, perhaps augmented by inertial, simply means I'm going to leverage the known dynamics of my platform against your attack. If you get the amplitude right, but you make me jump in position, I'll think, well, maybe things aren't quite right. Polarization discrimination, GPS received signal is right-hand circularly polarized. If you do something else, that's bad. Angle of arrival, if I use that beam steering antenna, I can afford it apparently on this platform, and your signal comes from the horizon and is emulating a satellite that I know full well is at 90 degrees amplitude, I'll get you on that. And then what we'll talk about here is a cryptographic approach.
So maybe I didn't understand your example.
Yeah.
I think in your example, this fishing boat was rebroadcasting a fake GPS signal.
Yes.
So how would any of those accept cryptographic authentication have any bearing on that example?
Yeah. I consider your comment a friendly comment. The concern, certainly voiced by O'Hanlon, is that yes, you can do these things, but all of them can be overcome with some effort. So let's talk about authenticating GPS. And to set that up, I'd just like to remind you of the normal operation of a GPS receiver. Here's the received signal. We sample that. It comes in with some Doppler shift and carrying a spread spectrum code that is shifted early or late. And so what we do is we wrap a frequency lock loop around this, wipe off the Doppler, and then wipe off the code. So essentially both of those operations are correlation. And this is all good. If we then integrate that product, we get the correlation and we just seek the peak. That's really the most atomic operation of the GPS receiver. The signal that we're usually talking about when we draw a drawing like that is this dark blue one. So here's the GPS spectrum. 1575.42 is L1, 1227.6 is L2. We have signals at two frequencies. The civil code is well known. It's just that. It's part of an open service. You can look it up. If you've taken the GPS course, you have built these code generators, and they're quite straightforward. The red is the military code, the PY code, which is at 10 times the chipping rate. Moreover, it's 1 week long. And it has this nice property that we're trying to leverage, which is that if I give you a snapshot of received PY code data, you can figure out where you are. If, on the other hand, I tell you where you are, it's darn hard to figure out what the PY codes should have been. It's a random sequence. It's a very long sequence. It's very deep in the noise, never mind that they're all on top of each other. So I don't mean to say it's impossible to go from lat long to PY codes, but it's hard, and it takes time. So that's the property we're trying to do something with. Here's the architecture. You sample your received data. You do it in a wider bandwidth, so you capture the PY code. And you just take that data and imagine just store it. It's your GPS PY signature. Later on, I might ask you for it. And the thing that I did was I stored PY code data at a network of stations around the globe. So I'll just take your sample, correlate it with my data that's stored, and by so doing, really do so-called codeless differential GPS. And by doing that, I can figure out where you are relative to me, just by a normal GPS nav solution. The cool thing about that is that there are a number of variations on the theme. It may not be wise for me to actually ask you to send your signature. That might be more risk than it's worth. So I can actually send you snippets of data and ask you to answer questions based on your own correlation of that snippet that I push at you. So architecturally, that may make more sense. And the other thing that's neat is you don't need to know the PY code. So there's no presumption or assumption here that I got the PY code from the military to do this correlation. In fact, I just recorded the same chunk of bandwidth that you did at the time. And let me emphasize that in this architecture, the device to be protected does not need to carry a GPS receiver. The GPS receiver may just have been in the factory at the time, and we pushed those signatures in. Here's an example. Some of the folks that are interested are the people who manufacture integrated circuits. And so their concern has to do with the provenance and the security of the supply chain for ICs. They're very worried that integrated circuits, when they come back to the buyer, contain malware or Trojans. They have a long list of concerns. And they feel that it would be helpful to inject the GPS signature at the time of manufacture. An integrated circuit is a nice host. We need about 100 kilobytes of memory, which they sometimes complain about and sometimes they don't. I don't know their field that well, but in some applications apparently that's imaginable and others it's not. And sometime later, at a different location, you're going to assert, I was manufactured at location X at a certain time. And that may have been the time when I had my on-site inspector there. I don't know all of the physical security that goes with this. And through this mechanism, I can authenticate whether that's true or not. This is one of those cases where, since it's authentication of a past time, you have to be a little careful about what you actually let out of the integrated circuit, because if someone persuades you to send you their signature and they're malevolent or there's a man in the middle, they just got your signature that's valid for that location and time. So you might instead want to push questions in. It's a very difficult problem. I certainly don't know the answer about how many questions you should ask to get the level of authentication that you want without more or less giving away what the signature is. So that's an open issue. Here's the idea of the integrated circuit propagating down its supply chain. And we may query it imaginably anywhere along that supply chain up until, including when it's actually installed in the printed circuit board, the CPU on the printed circuit board could imaginably do all this automatically and say, oh, I see that you want to be one of my peripherals. I don't date anybody. I'd like to know where and when you were manufactured. There are any number of a host of issues. I grew up in the safety community, and it's been fun to learn a little bit about the security community. And there's a running argument about who's more paranoid. Safety people are worried about accidental faults and what Mother Nature may do, and security people are more worried about what ill-intended person might do. I think right now it's about a tie. They're both extremely conservative, yeah?
Just another candidate might be Hollywood.
Yeah.
I guess there's going to be a unique active device to do aquarium, so straightforward DVD is not.
Yeah. You're right. I should have mentioned it. This is a server-based architecture, and that's a tricky issue in itself. You have to talk to the server. Hollywood has an interest because they want to do digital film distribution. These days, apparently, they ship, those famous reels around, and the cost is enormous, and the film itself doesn't last that long, so they would rather send it to you digitally, but boy, they worry about piracy. So they'd like to add location security as another level in their overall stack of security to say, oh, well, you're an authorized theater. Now, the one weird thing about location-based security is it's just that. It's location-based. If you and I have the same location, location-based security doesn't help at all. So there's some assumption about physical security that goes along with it. Summary. GPS really has become a new utility. I told already the story about 40,000 versus 500 million. Coverage and security remain as hard problems. Over the last 15 years, we've learned so much about the fault pathologies and the rare normal pathologies that I'm willing, so a little bit of a reach, to put safety in the win column. In other words, the integrity of the system can be assured. But security is still hard. Coverage is still hard. All the chip merchants are integrating GPS with Wi-Fi, Bluetooth, every imaginable thing, which is already part of the infrastructure to handle navigation indoors. In addition, we can't take our eye off the ball. Those 30 satellites are a precious resource, and they're more frail than you might think. We're just about to embark on a new block of satellites, so-called Block 2F. We're switching the satellite vendor, and so we're very concerned that those satellites will have the same 12-year lifetime as the ones from the previous generations. So we have to keep our eye on just sustaining the health of GPS at the same time. That's what I have for you today. I'll be happy to take any more questions.
So we do have a couple minutes for questions.
Well, I have one right here from our online web viewers. It says, how would this prevent a consolidation of PY codes? Are they reverse engineerable?
I kind of heard a couple of questions there. PY code, people have studied it quite a bit, and it's partially reverse engineerable. There's a so-called W code that lies under there, and people now understand how that multiplication is done. People in the civil community, certainly people in the military community understand it. But I don't think in general it's easy to reverse engineer it. What you could do, if you wanted to mount that kind of attack, is build an antenna farm where you tracked each satellite separately, and then you could reconstruct or re-engineer the data that would give that lat long. It turns out it's harder than you might think, because unless the antenna is very big, it's got a rather wide beam width, and you'll see the vestigial signals from the other satellites in there. So the astute authenticator could do something with that. Moreover, if it takes time, remember time is part of the GPS solution, and if it's a present time assertion about location, I can also check and make sure that you've got the present time correct as well. Yes, sir.
So is this just a case where was this just a case where the civil community is catching up with security developments that have already been realized in the military community?
That's a very good question, and I don't really know the answer. I would tend to say yes. But I am not a member of the military community, so I can't give you the sharp answer that perhaps you're seeking.
So I have a question right here.
Thanks for the wonderful talk. I'm wondering if you could say a little more about the cryptographic authentication. In particular, I didn't quite understand what would prevent a spoofer from recording this military signal and then replaying it with some delay. And if I understand correctly, I guess delaying the satellite signals appropriately could cause you to misestimate your location.
Oh, yeah. I mean, if you're willing to do all of that, I think that's the counterattack I was just talking about. You would have to receive each signal separately, because if you receive their aggregation, when I do the correlation, I'll see the multiple peaks. But if you do separate them spatially with a sharp, the antenna has to be 5 or 6 meters in diameter per satellite. Now, you might be able to implement that with a phased array, but it's still a big antenna. And then you could, by using the spatial characteristics, just receive each signal separately and do the reconstruction. I think that's more of an attack when I'm asserting my past location to you. If I'm asserting my current location to you, then the delay associated with that, I think, is so long that I could check on the time estimate associated with that data. Yes, sir.
Does the European system do anything any better than GPS does? And the other question is, can you use both of them together to prevent the kind of spoofing problems you're suggesting?
Those are two great questions. As a matter of fact, they relate back to your question. One of the strongest selling points of Galileo has been the security applications. They feel that's where GPS civil is weak, and so they should rush in there. So what they have done is included signatures in the transmission from the satellite. Given that we don't have that in GPS, we're having to emulate that by using the server. So that is a strength of Galileo. They haven't been very public about that function in the last couple of years. So I don't know where they stand on it technically. I know that part of their program, so-called Public Regulated Service, PRS, which is European speak for military, has moved far to the right in their schedule. So I don't know all of where they stand on that. Oh, and then the notion of using them together, yeah. But I think, imaginably the whole aggregation could be spoofed as well. So I think it's a step in the right direction, but I don't think it's decisive. Yes, sir?
Couldn't you just use some sort of majority model where you just reject any single source that's an outlier and just take information from most of the other sources that are reliable? Is that a possible way to remove spoofing?
That's a very good question. I should have included it on my list. We leverage the fact, or I think your idea would be, gosh, if you really have 7 or 8 satellites in view, your position estimate is overdetermined. And if that's the case, and they attack only a single signal, you can do a residuals check, isolate the signal that's being attacked, and discard it or at least detect it. So the modern spoofers emulate the entire constellation. We attack them all. Well, the idea is to attack them all.
Question? If you were...
Thank you.
If you were not constrained by the current system, PY codes and all, and we're designing de novo a location authentication system, perhaps that had physical characteristics like, say, antenna size, things like that.
Yeah.
How might you go about doing it and taking into account things like a minimal piece of trusted computing on the device that's doing it, maybe just correlation, XOR correlation, or something simple like that.
Yeah.
Who's working on that, and what would their approach be?
You've totally caught up to the current research effort. And we're submitting some patents on exactly that. So if you don't mind, I won't answer your question, but it's a very, very good question. And if you know the answer, could you send it to me? Yeah. So exactly. There are a lot of interesting issues, not only for satellite navigation, but terrestrial, if you want to design a signal to really serve this purpose well. You would do things differently, for sure.
Well, thank you very much for the wonderful talk, and please join me in thanking Professor Enge again.
Thank you.